Welcome to the video for section 2.2, Substitution and Elimination. In the previous section, we saw the idea of the solution of a system of equations. We found some solutions using our calculator, or just kind of intuition, as well as the table feature and graphing. In this section, we're going to see how to solve these systems algebraically. Now, this approach is much more powerful than using the table, especially. This will allow us to find less precise or less easily identifiable solutions, particularly solutions that are not integers. So the first approach, whose definition or procedure is given on page 33, is the substitution method. So what we do is begin by selecting one equation and one variable within that equation that is going to be easy to solve for. Now, in this case, the first equation we see, x minus y equals 2, is much simpler than our second equation, 8x plus 7y equals negative 119. So I'll choose the first equation, and I will solve for the easiest variable to solve for. In this case, I think x is going to be the easiest to get by itself. We can do it in one step by adding y to both sides. Okay, now the reason that the solution approach works is both of these equations have to be true. So if the first equation, or this version of it, is true, then we can think of this as an identity. We can say that x and this expression y plus 2 are interchangeable. We are holding that to be true. And what we do with that information is now we replace x in our other equation with y plus 2. So that equation becomes 8 times y plus 2 plus 7y equals negative 119. And this is what we were getting at. The reason that we're happy with this result is now I have a single equation involving a single variable. In this case, the one that's left is y. So I can solve this equation using the order of operations and manipulating the equation by adding or subtracting from both sides and other techniques. So the first thing I might do is simplify a little bit. I can multiply what's in the parentheses by 8, and I get 8y plus 16 plus 7y equals negative 119. And then I can combine like terms. 8y plus 7y is 15y. And finally, if I subtract 16 from both sides, I see that 15y equals negative 135. And if I divide both sides by 15, I see that y is equal to negative 9. So that is half the battle. Our solution point will have a y-coordinate of negative 9. So we've completed steps 1 through 3. Now we need to use what we know to figure out what x is. So I know that both of these equations must be true. So one option would be to plug that y value back into the first equation. So if we reverse substitute y equals negative 9, I see that that results in the implication that y plus 9 equals 2. If I subtract 9 from both sides, I see that x would appear to be negative 7. So that would be our solution. Now to check and verify that this really is a solution to the system, we would substitute x equals negative 7 and y equals negative 9 into both equations to make sure that they check out. So our first equation, if x is negative 7, is it true that negative 7 minus negative 9 equals 2? Well, you can think of this as negative 7 plus 9, which equals 2. Our second equation is going to involve a little bit more work. So if I plug negative 7 in for x and negative 9 in for y, is it true that the left-hand side evaluates to negative 119? Well, if we crunch some numbers and use the order of operations, the first thing I see is that negative 7 times 8 would be negative 56, and negative 9 times 7 would be negative plus negative 63. So, is negative 56 minus 63 negative 119? I believe it is. And we have satisfaction in both cases. So that is the substitution approach. In this case, our solution point did not represent any physical quantities, so we don't have to write a sentence describing what this solution means. But we do always want to write it as an ordered pair. This represents a point in space where these two lines that we began with intersect each other. You can confirm that by throwing it into your graphing calculator and seeing where those lines intersect. Since this solution point, negative 7, negative 9, lies within that standard window, we could do this pretty easily, although you are going to have to manipulate your equations a little bit in order to plug them in. So I will let you guys try that. If you have any questions about that process, bring them to class. So let's look at one more example of using substitution. If we have two equations, 5x plus 2y equals negative 14, and 4x minus 2y equals negative 40. The question now becomes which equation and which variable should we solve for? I will default to using the first equation, since it looks a little bit simpler to me, and I will try to solve for y. So to do that, I'll move the 5x over, 2y equals negative 5x minus 14, and divide both sides by 2 to get y alone. So y is equivalent to negative 5 over 2x minus 7. And what I'm going to do with that is replace y in the other equation with what y is known to be equal to. So this is step 2, the substitution part of the substitution method. My new equation is going to be 4x minus 2 times this quantity, negative 5 over 2x minus 7 equals negative 40. And from there, all that I need to do is solve for x. And the solution process will look very similar to the previous problem. If I distribute the 2, I see 4x minus 2 times negative 5 halves. Here we have negative, negative. That'll become plus some cancellation 5x. And negative 2 times negative 7 would give us positive 14. So make sure you're clear on how we ended up with all of that information. Negative 2 times negative 5 halves gives us 5. Negative 2 times negative 7 gives us 14. And if we combine some like terms, I have 9x. And if I subtract 14 to the other side, I see that this is equal to negative 54. So my new equation says 9x equals negative 54. If I divide both sides by 9, I see that x is equal to negative 6. So our solution point is halfway done, We think the x-coordinate is negative 6. All that remains is to find the y-coordinate. This time, it does not matter which equation you substitute back into, so I'll use the second equation just for kicks. Also because if I'm plugging x in, I would like to multiply it by as small a number as possible. So in the top equation I would be multiplying it by 5, in the bottom equation I am only multiplying it by 4. It's not a big difference, but it is a nice practice to get into the habit of. So step 4 I believe we are on, out of the process. We plug negative 6 into one of our two equations, does not matter which. And now we need to solve for y. So if I multiply this out, I see negative 24 minus 2y equals negative 40. If I add 24 to both sides, I see that negative 2y equals negative 16. And if I divide both sides by negative 2, I see that y equals 8. So our solution point, negative 6, 8. And we always want to verify that we did everything right. If I plug negative 6, 8 back into either equation, I should come up with a valid equality. So our first equation, if I substitute negative 6 in for x and 8 in for y, well, that would give me negative 30 and 16. So negative 30 plus 16 would give me negative 14, which is exactly what we wanted. Our second equation, if we plug negative 6 in for x and 8 in for y, that would give me negative 24 and negative 16. Negative 24 minus 16, which is negative 40, which is our goal. So our solution point, negative 6, 8, is valid. And that is the substitution process. So next we are going to look at elimination, and we're going to use the same equations so that we know if we've ended up with the right answer and we won't have to check them again. In this section, our second strategy for solving systems of equations is called elimination. Now, in this approach, we are aiming for the same goal, ultimately eliminating one variable, resulting in an equation involving only one variable and one equation and one unknown. So, I'll begin looking at the second system that we worked with in the previous part. Let me consider these two equations, 5x plus 2y minus 14 and 4x minus 2y equals negative 40. So with elimination, whose process is listed on page 34, we would like to rearrange the equations if necessary so that they are in standard form. We are already in that case for both equations, so we don't need to worry about that. If necessary, we need to multiply one equation or the other by some constant, or constants, in order to have the same coefficient, or the same magnitude coefficient with opposite signs on one variable. Again, I see that we already have that. Here in the y column, we have plus 2y and minus 2y. So all that we need to do at this point is add the left-hand side of our equations together. So if I add the left-hand side, I'll add my x's and get 9x, and I'll add 2y and negative 2y and get 0y. So we've eliminated the y variable. Now if I add negative 14 and 40, I get negative 54. And at this point, I can move on to step 2, solving this equation for the variable that remains, in this case x. So if I see that 9x equals negative 54, if I divide both sides by 9, I see that x equals negative 6, and we are in exactly the same place we were with the previous problem. So if x equals negative 6, what is y equal to? Well, we go back to one of our original equations. This time I'll use the top one, just to see how that would look. If I substitute negative 6 in for x, we see negative 30 plus 2y equals negative 14. So if I add 30 to both sides, I see 2y equals 16, so y equals 8. And we've already done the work of checking, but you would, if this were a new problem, always want to check your solution in both of the original equations. So that is the elimination method. And this was a very simple example. We didn't have to do much work with this one. So let's see another one where we might have to do a little bit of setup. So if we go back to the first equation, or system of equations that we saw in this section, remember we had x minus y equals 2, and 8x plus 7y equals negative 119. Alright, if we need to solve this by elimination, what I need to recognize is if I jump to adding the left-hand sides together, neither of my variables will be gone. I will have 9x and 6y. So what I need to do is multiply one or the other, or possibly both of my equations by some values, so that one of my variables will disappear. Now, we already saw one where we eliminated the y values. I'm going to do the opposite. I'm going to eliminate the x values in this problem. And I'm going to do that by multiplying the top equation by negative 8. So I'm going to try to get the coefficient of x to be the opposite of the coefficient of x in the second equation. Now, I'm not allowed to just multiply one side by negative 8. I'll multiply the right-hand side by negative 8 as well. So my new equation, which is equivalent to my old equation, looks like negative 8x. Negative 8 distributes to negative y, becoming plus 8y. And on the right-hand side, I have negative 16. My bottom equation is unchanged. I still have 8x plus 7y equals negative 119. At this point, if I add the left-hand sides together, negative 8x plus 8x eliminates x, and 8y plus 7y leaves me with 15y. And on the right-hand side, negative 16 plus negative 19 leaves me with negative 135. This should also look familiar. This equation was something we encountered during the solution process using the substitution method. If I divide both sides by 15, I will find that y equals negative 9. And again, I now need to substitute that back into one or the other of my equations to determine what x has to be. So if I solve the rest of this in exactly the same way as we did before, I would substitute y equals negative 9 into my original top equation. Just to change it up, I'll substitute it into the bottom equation instead. So we can go about it in this way. It might not be as nice of a solution process. So 8x, 7 times negative 9 would give us negative 63 and negative 119. If I add 63 to both sides of this equation to isolate the 8x term, I see that 8x equals negative 56. And if I divide both sides by 8, I see that x equals negative 7. And again, that matches with the solution we found using the substitution process. but if this were a new system of equations, I would always want to check my work. We would do that by substituting -7 and -9 into both of the original equations and making sure that everything checks out. So that is all that I will say about how to go about the elimination process. You should get started on those homework problems. I do want to look at the strange cases in this section. So far, we have only encountered systems of equations that had exactly one solution point. These lines cross, and they cross at one point. That is not the only possibility. In the previous section, in the notes, it is mentioned that we could encounter parallel lines. If our lines are parallel and are distinct from each other, then they will never cross in 2D space. On the other hand, it's a strange case to discuss, but sometimes we are given a system where our lines may not look like the same thing, but they turn out to be, in which case, if we were to graph both of them, they would overlap forever. They would be the same line, and every point on one would be on the other, and there would be infinitely many solutions. So the way that we determine if that's the case using these solution techniques, rather than attempting to graph and visualize which case we're in Theorem 2.4 in the notes, on page 34 as well, there are two possibilities. If, using either one of these solution approaches, if both variables cancel, if we are left with an equation involving neither variable, one possibility is that the resulting equation is a contradiction, something along the lines of 0 equals 1, or 5 equals 10, or something strange like that that is obviously false. If we encounter something like that, then we would infer that these lines were parallel and distinct from each other. They're different lines that never cross. There is no solution to be found from that system. On the other hand, if both of our variables cancel again, and we are left with an equation that is obviously canonically true, referring back to the terminology section at the beginning of the notes, we call these types of equations identities, something along the lines of 0 equals 0 or 1 equals 1, something that is irrefutably true. That implies that the two lines in question are identical. They are the same exact line. An example of one of these would be the system that we see in this example. We are going to solve this, or attempt to solve, using elimination. So the first thing that we need to do is get both of these into the standard form ax plus by equals c. They are both already in that form, so our x's are over the x's and our y's are over the y's, and the constant's over the constant. Next, we need one of these two variables to have matching coefficients in the top and bottom equations. So I will try to use the x variable. I will multiply this by 2. So my new equation, 2x plus 2y equals -10. My bottom equation, -2x minus 2y equals +10. Now if I add the left-hand sides, I have 2x minus 2x, that gives me no x's. 2y minus 2y gives me no y's. And -10 plus 10 gives me 0. The resulting equation contains no variables, and it says that 0 equals 0. This is canonically true. This is what we would call an identity. So these lines are the same. There are therefore infinitely many solutions. As an example, let me see. Our original system was x plus y equals -5 and negative 2x minus 2y equals 10. So a solution point to either equation will be a solution to the other. So for example, if I let x be 0 and y be -5, that would be a solution to our top equation, right? 0 minus 5 equals -5. And it will be a solution to our bottom equation. So -2 times 0 minus 2 times -5. -2 times 0 vanishes, and -2 times -5 equals 10. So this is a solution. Additionally, if we let x be 1 and y be -6, let's see what we end up with in that case. Well, that's a solution to our first equation. 1 minus 6 would give us -5. And -2 times 1 minus 2 times -6 would be -2 plus 12, which also gives us 10. So here we have two solutions to this system of linear equations, and in fact, any point on our first line will also lie on our second line. Another way to see this would be to put both lines in slope-intercept form. So our first line, if we subtract x over to the other side, we get y equals -x minus 5. Our second line, if we add 2x to both sides, we see -2y equals 2x plus 10. If I divide both sides by -2, my second equation is therefore y equals -x minus 5. So they are exactly the same line if we write it in these terms, and it's easier to see why these lines overlap with each other. So the short answer here, if we come up with an identity, an equation that is never false, then these lines are exactly the same and we have infinitely many solutions. Every point on either line is a solution. Here we'll solve a slightly different system, similar in shape but with a few things rearranged, using the other method. We'll solve this using substitution. Now I'll pick an easy equation and an easy variable to solve for, and it looks as though x will be pretty easy to solve for in the top equation. So if I isolate x by moving y to the other side, by subtracting it, then I will substitute that, -y plus 10, for x in my bottom equation. -2 times -y plus 10 minus 2y equals -5. I'll then attempt to solve this equation for y. So we see 2y minus 20 minus 2y equals -5. Now again, following the same reasoning, if I attempt to combine like terms, if I take 2y and I subtract 2y, I see I have -20 equals -5. Now, in no possible universe is that the case. This is a contradiction. So there are no solutions. The reason that we arrived at this contradiction is that these two lines are parallel and distinct from each other. You can see that if you put them in slope-intercept form. Our first line would look like y equals -x plus 10. Our second line, if we move 2x to the other side and divide both sides by -2, we would get y equals -x. See, we have the same slope there, but our y-intercept is very different. -5 over -2 gives us 5 halves for our y-intercept. So we have the same slope and different y-intercepts, which means these lines are going to run parallel to each other forever, never crossing and never affording us a solution to that system. So those are the two strange possibilities in this section, and that is what to watch out for. Using either method, if your variables disappear, which case are you in? So that is it for 2.2. Go ahead and get started on all those homework problems and bring any questions you have to class.